Thank you, David, for the introduction, and hello, everyone. It's my pleasure to share with you today some exciting galaxy evolution pathways that my group has uncovered in galaxy clusters, and I would like to particularly highlight the work that David Sobral, my collaborator, has done, and also the students who work with me on these projects, Joe Cairns, who's also here at the conference, Miriam Husseini, and Courtney Canning. And in understanding galaxy evolutionary pathways in clusters, I will focus on today on contrasting relaxed cluster environments and disturbed clusters that are undergoing a major growth phase. And we believe, as Matt said, that cluster mergers may provide a fundamentally different environment for galaxy evolution. They are the most energetic events since the Big Bang. Huge amounts of energy are being released in the form of shocks and turbulence and very strong tidal fields. And one thing that is very important to note is that cluster mergers are actually quite a significant population. About 50% of clusters at redshifts below 1 are actually undergoing mergers. And knowing that every local cluster has undergone at least one major merger in its history, it is therefore very important to understand the complete picture of galaxy clusters, both the relaxed and the mergers, to be able to understand galaxy evolution as a whole from the perspective of environment. And to understand these questions, well, to address these questions, I embarked on an ambitious observing campaign to unveil the evolutionary pathways in galaxies in the large-scale structure of 19 relaxed emerging galaxy clusters located at a redshift of about 0.2. And I called this project ENISALA as a tribute to the ENISALA citadel near my hometown in Romania. And the goal for the project was really to study the life cycle of star formation in clusters, look at the recent star formation black hole activity through optical emission lines such as H-alpha, connect that with star formation on longer timescales by looking at supernovae, and also measure the reservoirs of gas that could fuel star formation activity in the future. And, you know, in 2017, when we first had the first edition of the conference, we had just completed the largest H-alpha narrowband survey of our 19 galaxy clusters, which enabled us to uniformly select star-forming galaxies and AGN. And we found striking differences between the relaxed and merging clusters, with mergers having significant overdensities of star-forming galaxies compared to their relaxed counterparts. And for comparison, we also conducted the widest narrowband survey of H-alpha in 3 different extragalactic fields, thus overcoming cosmic variance. However, in the 26 square degrees that we covered in our survey, we found no field is as dense in star-forming galaxies as the merging clusters, indicating that mergers are very special parts of the universe. But since 2017, we were very interested to understand the causes of this increased star formation activity in merging clusters, and also understand its relationship to the suppressed star formation that is expected in relaxed clusters. So the second part of the ENISALA project focuses on follow-up spectroscopy of emission line galaxies selected through our H-alpha narrowband survey. Using 4 different instruments, we covered 800 galaxies, including a broad selection of sources in a subset of our 14 merging and relaxed clusters. To aid in this project, I also designed Gleam, a state-of-the-art user-friendly parallel Python package for fitting Gaussian models to emission and absorption lines in large samples of 1D spectra. So if you think that that might be useful for you, I encourage you to check out our GitHub page and also the associated paper. And to illustrate the quality of our data, I'm showing you here a multi-wavelength view of Abell 2254, a massive 2 × 10⁻15 solar mass cluster undergoing a major merger which injects turbulence in the intercluster medium. And all of these filled symbols show confirmed H-alpha candidates that have spectroscopy available through our project. So now that you're familiar with the sample, let's jump into some of the results. I'm showing you here the probability distribution where a galaxy is located with respect to cluster-centric distance divided by ionization source, so whether the H-alpha is coming from star formation or from black hole activity, and separated by cluster relaxation status. And again, we find surprising differences between merging and relaxed clusters. We find that the bulk of star formation and AGN activity in mergers is actually happening quite close to the core. So this is indicating a rich environment of subgroups and maybe filaments, and also gas-rich active galaxies that survive and can live maybe even towards the core of the cluster. By contrast, in relaxed clusters, the bulk of the activity is happening away from the core. And we actually find evidence for a triggering of black hole activity and star formation in the infall region of these relaxed clusters, which was found, of course, in other studies as well. So the idea would be that ground pressure can remove gas from these infalling galaxies, and this can be then triggered to form stars behind the galaxy, but part of the gas can fall back onto the galaxy and fuel black hole activity. Our galaxies also have very different properties as a function of galaxy color. Of course, we find that on average, star-forming galaxies are bluer than AGN, but we find a particularly blue population of galaxies, particularly in merging galaxy clusters. And these galaxies and mergers also have higher equivalent widths at all galaxy colors by a factor of about 1.5 compared to counterparts in relaxed clusters. And we know that equivalent width roughly correlates with specific star formation rate. So the idea would be that these are low mass galaxies with large equivalent widths and large specific star formation rates. And really, maybe the most consequential finding of this work is that merging clusters seem to host a population of these continuum faint star-forming galaxies with bright H-alpha emission lines, which simply doesn't seem to exist as much in relaxed clusters. And this population of faint galaxies with high equivalent widths, high specific star formation rates, they also have low metallicity. So this really supports a scenario in which these low mass galaxies are actually experiencing a triggered star formation episode, and we're basically seeing them as they're building up their stellar mass. And Matt already previewed this. I wanted to kind of address the question, okay, what is actually triggering this activity in merging clusters? And this is the sausage cluster. It's a very interesting object because it's gone through a major merger about 0.5 to 1 billion years ago. It has massive shock waves traveling through the intercluster medium, and it also hosts a spectacular overdensity of star-forming galaxies, 20 times above a typical field at its redshift of 0.2. And together with Miriam Husseini, we followed up 5 galaxies in the sausage cluster with resolved integral field spectroscopy, maybe providing us the first resolved view of these possibly shocked cluster galaxies. And we find really interesting results. Our galaxies have atypical H-alpha flux, H-alpha velocity, and metallicity properties, with galaxies having tails of emission outside of the stellar disk. They also have asymmetric rotation patterns in H-alpha, and also metallicity gradients, which are actually more aligned with the stellar disk of the galaxy, the ionized tails of the galaxies, and actually the merger axis of the cluster, providing us maybe the most direct connection to date between cluster mergers and star formation triggering. But if these disturbed clusters have lots of star formation on short time scales, what is fueling it? What is fueling star formation in these merging clusters? And have these star-forming galaxies used up all of their gas, and do they have any fuel left for future star formation episodes? And we wanted to address exactly this question with Joe Cairns as part of his PhD. We conducted a molecular gas survey of Antlia, which is the most nearby disturbed galaxy cluster that we know of. And what this molecular gas survey showed us is that actually cluster galaxies and field galaxies sit on the same stellar mass star formation rate molecular gas plane. So if you take a galaxy of a similar mass, similar star formation rate in clusters and the field, it has just as much molecular gas. So this might be because Antlia is an intermediate environment between a field and a truly relaxed local cluster. So this gentler environment, maybe not necessarily gentle, but this intermediate environment allows galaxies to retain their gas for longer. And maybe this evolving intercluster medium is just starting to interact with the member galaxies, producing the first evidence of maybe triggered star formation, and also the first evidence of quenching. And, if we put together the detailed spectroscopic analysis of the ENISALA survey combined with these gas tracers, this enables us to maybe break degeneracies between different models that have been proposed for galaxy evolution in clusters. And it seems like we uncovered pretty strong evidence that cluster growth correlates with which effects are the strongest. And our results are actually readily explained by a model that was proposed by Ebeling and Kalita in 2019, in which gas-rich galaxies infall along filaments in the rich cosmic web that surrounds these merging galaxy clusters. And this is followed by trigger star formation. And this disrupted merger environment, as I mentioned, is permeated by the shock, the turbulence, the gravitational tidal fields, and these can all act as catalysts for triggering star formation in gas clouds, as well as funnel gas into the galaxy center, causing accretion onto the black hole and promoting AGN activity. The scenario can also lead to a sharp rise of star formation between 100 and 500 million years, which is very compatible with these high specific star formation rate galaxies that we find almost exclusively in merging clusters. Now, by contrast, we do find evidence for a mild enhancement of AGN and star formation at the outskirts of relaxed clusters. And this is followed by a dearth of star formation towards their core. So these observations definitely support very well-established models that invoke mild ramp pressure triggering activity at large radii, followed by very rapid quenching taking over as the infalling galaxy crosses the cluster core. And I would like just to finish by highlighting some interesting similarities between these lowered redshift, redshift 0.2, 0.3 merging clusters and high redshift protoclusters and clusters. Both types of objects are in the process of formation. However, there's some very important distinctions as well. Low redshift mergers have a much higher mass and a clear intercluster medium. But I would still be remiss if I didn't point out the massive similarities between the mergers and the high redshift protoclusters. Both have high fractions of star-forming galaxies. Their cluster galaxies form stars at the same rate as field galaxies, have high gas fractions, and maybe even widespread molecular gas reservoirs. So we'd just like to leave you with my takeaway message, which is that evolving from a field to a relaxed cluster environment is a very chaotic process involving accretion, collapse of filaments, and mergers. And these merging clusters might be a population that displays a reversal of the typical environmental trends that we are used to at low redshift. And mergers at low redshift might even tell us something about high redshift clusters, which is very exciting. I'm also very excited for the next 2 years, where I will explore the ENISALA survey to probe the detailed physics of the star-forming galaxies and active black holes in our clusters. And also in the next 10 years, we're going to have such exciting telescopes coming online, which will help us place galaxy evolution in the context of the intercluster medium and the filamentary structure that surrounds clusters. And with this, I will say thank you, and I will take any questions. Thank you.